Well, this is the second video discussing the electrophilic addition reactions to alkenes. In the first one, we looked at inorganic acids that have, a halogen on the second step that can add to the carbocation. The first step involved the attack of the proton. So we're not going to change too much as we go to 2, because in 2 we're going to use an acid, but instead of having just an inorganic acid like HBr, what we're going to do is add acid and have just a catalytic amount of this acid and a lot of water or solvent that can come in as the nucleophile in the second step. So very, very similar to what we've seen in first reaction 1A, where we had Markovnikov addition of HBr, HI, HCl in the first step attacking a proton. We're still going to attack a proton, but we'll use maybe sulfuric acid, nitric acid, or some other small amount of acid. And then we'll follow up with an attack with water. Water being used as a nucleophile in the second step. So very, very similar mechanisms between 1A and 2A. Acid catalyzed hydration and Markovnikov addition of a HBr, HI, or HCl. In number 2B, very different, we'll be using BH3 or or variations thereof in a second reaction. So there'll be a 1 and then a 2 where we use peroxides and base. So there's going to be a 2, separate reactions for hydroboration, oxidation. So there's, in 2B here, a way we can add water still across an alkene, but in an opposite anti-Markovnikov manner to 2A. So 2A and 2B give you addition of water across the double bond, but in different ways. This is Markovnikov. This will be, in terms of addition of water, anti-Markovnikov. And then we'll finish with 3A and 3B, which are, different altogether, because what we're doing in 3A is we're adding just Br2, usually Br2 or Cl2, are used as the reagent, Br2 or Cl2. It's called dihalide formation that we have, or it's a addition of Br2 across the double bond to make a dihalide. This is called a vicinal dihalide because the two halogens are not off the same carbon, but off of adjoining carbons. We call that a vicinal dihalide. And just like we have acid and then acid with water, we're going to have halogens and then halogens with water. So we're using aqueous solution here to change the second step, just like we used aqueous solution here to change the second step of acid addition across a double bond. We added acid, acid with water, Br2 or Cl2, Cl2 with water. That's what we'll focus on in this second video. Lots to cover. Really, we have 3 reactions. We have acid catalyzed hydration, hydroboration oxidation, and then really addition of halogens where only the second step differs in this 3B. So let's go to these 3 different types of reactions. We've already talked again about how acid reacts with the double bond. We have to go to carbocation. We have to use Markovnikov's rule. So for example, here we have water, but we have a catalytic amount of the acid. And if I don't know about you, but if I had to pick one of these 3 I don't want to drink, it would be the acid. I would drink water and an alkene before I'd drink some 6 molar acid or something like that that's been added drop-wise to some solution. So we only have drops to mils, spit to cups of this and this. We have a spit amount of this, but it's still reactive. So let's hit it. We hit it with what? Well, we only have pi electrons, just like before. Any face, or either face, the front or the back. We're, again, treating this double bond as having electron density in front of the paper and behind the paper. We can attack that proton, put the proton on the double bond according to Markovnikov rule. Let's review that. Place the proton on the carbon, here or here, that has the most hydrogens. Well, that would be this one. So the positive charge, by extension, will always be on the other carbon, which will be a tertiary carbon, carbocation. That would be stable. So we're not going to shift. We're going to attack this in the second step, not with the corresponding anion from the acid. We only have a spit amount of that, meaning we could have used for the acid here sulfuric acid, hydrochloric acid, but we're not going to use the anion that would be left after, or with, I guess, coming with that proton. We're going to use the excess of water, not because it's a much greater, better nucleophile, but we just have more of it. So this is going to come in and make the attack. We see that here. We go from owning two lone pairs to sharing them, so he becomes positively charged. He goes from owning to sharing, so he's going to have 3 bonds off of him. He'll have a positive charge. And we regenerate the catalytic amount of acid by getting our final product formed from this cationic state of oxygen. So this is called an oxonium ion. And our last step is going to be transformation of the oxonium ion to a hydronium ion and our final product. Some notes. So there you go. This is our small variation on acid addition across to pi bond. Well, what did we do to change it? We just had some excess water. We could have also used an alcohol where we have an R here instead of a hydrogen, an alkyl group. We still have to have at least one acidic proton in the oxonium ion that can be torn off. So we can't have ROR. We have to have at least one proton that we can rip off. So we can use, instead of water, you could use methanol as a solvent to attack in that second step. Some other notes: increasing the amount of water increases product formation, but if we want the reverse reaction, we could simply increase the amount of alcohol here, and we could have our acid catalyze elimination and maybe increase heat. So this is a reversible reaction. Please know that. You could actually reverse this if we wanted to go and make alkene from the alcohol. We could have a high concentration of alcohol. If we wanted to go the other way, have a high concentration of water to drive the reaction to the right. High temperature would favor elimination, so that would, if we went above the heat needed for just the reaction, we could go back to the alkene. Other things, just remember we had to regenerate that hydronium ion. It is the catalyst. And what are the acids that are typically used? Or H2SO4, catalytic amount. You can get away with HCl, but of course there'd be the danger that the chloride left over is somewhat nucleophilic. How do we work against that? We keep it at spit amount to cups of this. So small amounts of the catalyst. Well, that's our first reaction. Let's look at this one that's a addition of water, but through hydroboration oxidation, a very different mechanism. Only thing I do want to say is, I guess, similar, is that we still have to treat this first attack of boron through Markovnikov rule. We're going to still place the boron on the carbon that has the most hydrogens. Why? Because that boron in BH3 is still the electrophilic site, and we can still then use the Markovnikov rule, place the boron, which is the electrophilic site, not protons. This is not the electrophilic site. Please remember, BH3 or variations thereof, it's the boron that's the electrophilic site. So what we do is we place that on the carbon with the most hydrogens, and then in the second step, just know that the OH replaces the boron where it sits. So let's look at that. So the boron is attacked. It has an empty p orbital. That's why it's attacked. If you look at the electronic structure, there's a missing pair of electrons. It has only 3 pairs of electrons. That's why it's a very good Lewis acid. And we can fill up the empty p orbital from the top or the bottom, but either way, we start to make that attack. And at the same time, we're attacking this boron. One of the hydrogens is sliding over to the other carbon. It's a syn reaction. Syn meaning it happens that the boron and the hydrogen are on the same side. A transfer across that double bond in one step. The boron going to the carbon that has the most hydrogens, according to Markovnikov rule, and the hydrogen from the BH3 on the same side going to the other carbon. Now in the last step, I'm not going to discuss it mechanistically, though we did look at just briefly this mechanism. Just know, excuse me, man, my voice. Just know that the BH2, or the alkyl boron, sometimes this will be in a alkyl form where it has BHR2. Whatever it is, the boron-carbon bond will be broken, and you'll place where it sits, exactly where it sits, not only constitutionally, but stereochemically. You'll replace this with an OH. Where it sits, exactly where it sits, replace it with an OH. So let's put some notes down and move on. The boron in BH3 is the electrophilic site. We said that at the very beginning. Yet, it is replaced in the second step by OH. That's sort of the reaction. What then it appears to be in the end, where we land as a product, it appears as an anti-Markovnikov addition of water. Look at the starting alkene, and then look at the final product. It appears as if the proton in water, so if we look at the product, went to the carbon with the most, or the least hydrogens, and the OH went to the carbon with the most hydrogens. But it's just an appearance in anti-Markovnikov. So in the end, it's anti-Markovnikov addition of water. But mechanistically, it wasn't. So it's kind of hard for students to understand, but we're just saying from beginning to end, we call it an anti-Markovnikov addition of water. It appears that way, but we know in mechanism, we still attacked an electrophile, boron. We put it on the carbon with the most hydrogens, and it only appears anti-Markovnikov because in the second reaction, we replace the boron where it sits with an OH. Here's more on that first step that's so important in the hydroboration oxidation, the first reaction step. We say we attack again the boron, and we place the boron, because it's the electrophilic site, on the carbon with the most hydrogens. So in this alkene we have 2 hydrogens here. This has none off of this carbon, so the boron would go here. It's a syn addition, meaning that hydrogen from the boron on this other for the other carbon on the same side bonds. So we end up in the first reaction having what we call hydroboration, or alkyl borane formed. And then where it sits, replace BH2, or whatever that boron species is, with OH. Replace it, just where it sits. So in the notes from Paula Bruce, her organic chemistry textbook, she says Markovnikov's rule is followed in this reaction, and the reason the products of apparent anti-Markovnikov addition of water are obtained is because of the reagents used. So she even mentions that if you look at the reaction mechanism, it's still following Markovnikov rule. The boron is going to the carbon with the most hydrogens, but it's just an apparent anti-Markovnikov addition of water because of what we see in the end. The boron is replaced with the OH. I think that's good to remember. All right, that's our second one. Even so, please know we are going to call this anti-Markovnikov addition of water because we're looking at the very end. But that's our second one. Let's look at our third reaction using Br2 or Cl2 or Br2 Cl2 with water. Addition of halogens to a ring. Now the reason these are reactive, we don't need an acid catalyst like we've been seeing before, or a Lewis acid like BH3. These are very reactive. Br2 is reactive because you have a very weak bromine-bromine bond, or Cl-Cl bond. And it has, we need to put this out there right at the beginning, polarizability, meaning this bond, it's weak, and in solution, Br2 can have partial positive and partial negative ends in a dynamic manner in time. So we can hit one of the bromines and break the electrons in the weak bond back to the other bromine to make bromide. Now, what's different here is we do not have a carbocation. We didn't have one with BH3 because of the syn addition across the double bond in a single step, and we don't have one here, so no chance for a rearrangement for this one. Just like with hydroboration, we do not have a carbocation. As we make this attack, a halonium ion is formed. This is a kind of a different, I guess, from what students might expect. Bromine usually only has one bond, but the reason we don't have a single bond and a carbocation is because of, I'm just going to draw a little bit of a, maybe a, just giving some context here. If we were to try to put just the bromine on one of these two carbons, we'd have to put the positive charge right next to it. This carbon would have a bond to bromine. One of these carbons would have a positive charge since we're using 2 electrons to bond to the bromine. But the problem is this bromine has a lot of extra electron density that can fill that hole. So if we had a positive charge here, it would be immediately filled with lone pair electrons on the bromine. So we don't even consider this as an intermediate. We just draw the intermediate here called the halonium ion. This binds that positive charge on the, if you were to, I guess, propose it, it would bind that carbon, and we do not then have a positive carbon, i.e. a carbocation. We have a bromonium ion, where the positive charge is assigned to the bromine. This is somewhat different. It's very helpful in reactions to have this halonium ion. Why? Well, first, if you don't have a carbocation, you don't have carbocation rearrangement. And second, this is important, stereochemically, when I come in the second step, I don't come in on the same side as this, where this bromine sits in the bromonium ion. I come in from the opposite side. So it's very stereo-specific to what we call anti-addition. We've seen syn addition across the same side. The reaction is across the same side. Here the reaction we have in the second step across the other side. So we get a anti-addition of 2 bromines. This is our product. Br2 addition across an alkene. We go through the bromonium ion. You really want to remember that intermediate. And in the second step, the other bromine as bromide comes in from the opposite side. Now it could have come in here, or it could have come in here, because we don't have any selectivity by Markovnikov rule. We don't have selectivity like we'll see on the next slide. But we have to have anti-addition. So your other product could have been here, we could have had this bromine come in from the other side. I'm just going to show the top view here. And we could have had this bromine, which is on the bottom side. We could have had it on the right instead of on the left. So these are actually 2 enantiomers that are formed. This one is shown, and you're needing to write this one in. All right. Again, Br2 is able to react because of its polarizability, its weak bond. We want to remember that syn addition is blocked, so we have to have anti-addition. Anti-addition when we consider the second step to put the other bromine on. In trying to apply the Markovnikov rule, we see that for this particular one, we can't apply it. We just don't have a differing number of hydrogens. We'll have that on the next slide. We have one hydrogen here and one hydrogen here. That, I guess, limited us into what we could define in the second step. We couldn't say, well, this bromine, the original electrophile, has to be here or here. It didn't have to be. It could be connected in the end to either one, so we had it here on the left or here on the right. There is no selectivity. You have to go and consider both directions. The next one here will have selectivity. We'll have, oh, I see that this bromine, NBr2, is going to end up on the carbon with the most hydrogens. This has one, this has none. So in the end, I'm thinking this original bromine that I attacked to make the bromonium ion will be on the left side. So let's jump to that point. I'm going to then hit from the opposite side because I'm coming in anti. I'm going to hit from the opposite side, and this bromine was the original electrophilic site. I put it on the carbon that has the most hydrogens. So he swings to the left. This comes in on the carbon to the right, and we still have our anti-addition. Now, in this case, the anti-addition is not locked in to give us just trans product. It's not locked in, so sometimes you'll be seeing this drawn where these are across from each other in the product. But please remember, if this comes from a reaction of Br2 and an alkene, they come on anti to each other, but it's just not locked in conformation. So that's important. Markovnikov's rule is followed. The electrophilic site attaches to the carbon with the most hydrogens. We saw that. There is regioselectivity then in this second step. Unlike what we saw here, there was no regioselectivity. It could have hit here and give us this product, or it could have hit here to give us this product. Here we had regioselectivity, and we always have selectivity. It's very, very selective, though. We always come in from the opposite side. It just doesn't have to be always locked in. Here it's not locked in to a trans product. Here, because of the ring, these would be always on opposite sides. They would be locked in to a trans arrangement. We're almost done. We have just 2 more slides. Looking at now, just building on where we've been. We've looked at 3 reactions: addition of acid and water, hydroboration oxidation, and our last one, trying to get my finger out there, is Br2, or we can have Br2 with water. Let's try to, in the last 5 minutes, just look at a very general rule over all reactions, and we've hit it already. Achiral reagents give us an achiral product or a racemic mixture. So let's come back to Br2, and I guess this would be a 2-methyl butene. Let's take this 2-methyl butene and we attack the Br2. We make the bromonium ion. That bromonium ion. Okay, there we need to change that here. Bromonium ion. And we look at that second step. Do we have regioselectivity? Yes. This bromide can come in and attack specifically this one because the original electrophilic site is going to go to the carbon with the most hydrogens. So we're going to come in and attack here and push this to the left. But what we're showing here as our product has a chirality center. So this would be, if we look at chirality, a 1, a 2, a 3. So 1, 2, 3, 1, 2, 3 to the H to the back. So this would be an S. We have a chiral product. Not with the carbon here, that has 2 methyl groups off of it, but this one here. So what we have to remember is that the stereochemical rule is achiral reagents, achiral alkene, achiral Br2, have to give us an achiral product or racemic mixture. So I don't even care how it forms, but I have to have the enantiomer of this in a 50-50 mix. This plus this in a 50-50 mix. Now the way in which we achieve that I can show mechanistically, but please remember you have to have the ability to form these two if you have achiral reagents. So you have to have these formed in the end. Let's look at how this bottom one could have formed. Remember how we said at the very beginning of our discussion of alkenes you have two faces? We put this on the bottom face, but we could have just as easily put this original electrophile in a bromonium ion where it's not across the bottom face but across the top face. So this was bottom face. We could have had it on the top. Then we still come in selectively towards the carbon that has the most alkyl groups because this has to go to the carbon with the most hydrogens. And if we break that, then, we do get that other enantiomer. So it was really two different structures here. These are actually enantiomers at this point. You cannot make this look exactly like this. Regardless, please remember, if you have a chiral product, just draw its enantiomer. You can find the mechanism to get there, but there's got to be a mechanism to get there. All right, we're almost done. It's a long video. Here we go. Last one. We finally added water to Br2. We'd said, hey, this is not just Br2 with an alkene. We have Br2 with water. That gives us what we call a halohydrin, BrOH, formed across the double bond or added across the double bond. So we still do first things first. We still make a halonium ion. We don't have the bromide coming in the second step. What we're trying to do is have excess amount of the water to compete with that bromide to make an attack on one of these two carbons. And again, there's no stereoselectivity by Markovnikov rule here. We can hit this carbon with water or this carbon with water. And again, why are we doing this? Because we just added an excess of it, or at least equivalent amount, probably more, so that we can have competing reaction of water with this carbon competing with bromide hitting this carbon. So we get our oxonium ion. We have one equivalent of water coming in and acting as a base, so we get this hydronium ion. We get our halohydrin product. Is there regioselectivity it's asking in the second step? There was not. We could have hit this carbon too. We have a chiral product. This is achiral. This is achiral. So we have a chiral product. What must we draw for this chiral product? Since we know we can't have achiral reagents forming chiral products, we have to draw the enantiomer. So we could do that very quickly. I'll go ahead and try to keep the representation here as this is coming out towards us by drawing the bromine on top side and that OH on the bottom. So how do you get to this? Remember back here we don't have regioselectivity, so we could have come in here and attacked, and the water then would be up and to the left instead of up and to the right, and you can flip that over and you make this as your second product. These are the two products, two chiral products in 50-50 ratio formed from these achiral reagents. Alright, just to finish up, oxygen was the nucleophile competing with bromide to hit that carbon. It's not that it's more nucleophilic, but because we had a high concentration of water, it can form the halohydrin. The mechanism is very similar to that seen for addition of X2 to a double bond. It's just the second step differs. And we had formation of hydronium ion, H3O+. And, I didn't show it here, but we have this being left over, so our bromide or chloride is balancing that charge. Well, that's it. It's a long video on 3 reactions that we've covered. The addition of acid with water, addition of hydroboration oxidation, and then we've had Br2 or Br2 with water. Bye-bye.